that you get undressed. I hear symphonies in my head. I wrote this song just looking at you. Oh, oh. Yeah, the drums they swing low and the trumpets they go. And the trumpets they go. Yeah, the trumpets they go.
Okay class, today we're gonna look at a binary counter using 4 JK flip-flops. This counter converts the user input over here into a binary representation using 4 LEDs that are connected to the Q output for each flip-flop. And then it also has a reset switch here that will set the counter to 0.
Professor, what can this count up to?
This one can count up to 9, and then it'll reset to 0 once you go past 9.
Hi class, how's it going? Today we're going to talk about the JK flip-flop aspect of the circuit. So the JK flip-flops are really important because they're basically what allows the counter to work and the LED lights to have the correct output. So every time you press a button, it's fed into the clock input of the JK flip-flop, and then the output, the Q1, is going to be fed into the next clock input, and this is going to carry on throughout all of the JK flip-flops. And this is important because it staggers the output of the flip-flops in such a way that it will count in binary. So for like a quick example, if this is your clock, and then, so assuming that your JK flip-flops are positive edge triggered, which means that they are going to be triggered every time you have like an edge going from 0 to 1. What's going to happen is the output of the next flip-flop is going to follow something like this. So it's going to be triggered on the positive edge, and then it will go down on the next positive edge, and triggered like so. And then the next flip-flop is gonna do the same thing. So triggered like this. And if I was to continue this, like one more time, it would just like keep following this pattern. And that is really important because what's gonna happen is if this comes in like 0, 1, 0, 1, 0, 1, this is going to be like 0, 1, 0, 1, but it's going to be like the intervals, the frequency of the intervals is going to be half as much, and it's going to stagger it in such a way that you get a binary count. So like 0, 0, 0, 0, 0, 1, all the way down to 1, 1, 1. And that's just for like 3 flip-flops. If you would have 4, like we have, it would go all the way up from 0, 0, 0, to 1, 1, 1, 1. So our circuit should technically be able to count up to 15, but since we set it using the NAND gates at 9, it only counts up to 9. And that is why the JK flip-flops are really important in making this counter. Thank you.
Hello class, today we're going to be talking about NAND gates, so let's just get right into it. Alright, so we've talked about this circuit previously. It's going to be the 4-bit counter. And today we're going to be talking about all of the NAND gates and the purpose of the clear within the JK flip-flops. So overview, this is essentially the reset switch. So the clears are working all together to feed into the reset switch so that it guarantees once the counter is at 10, it will reset to 0. Right? So since it resets at 10, 9 is the highest number you can show through the binary LEDs. So why do we have so many NOT and NAND gates? Well, while we were building this in the lab, we didn't have access to AND gates, so we had to change the logic of our circuit to work with NAND gates instead. So for some of these, the NAND gate works fine, but for others, where we have a NOT and the NAND gate, that was essentially an AND gate primarily, but using the NAND gate with the NOT gate, we can function it as an AND gate without actually using an AND gate. So here we have the reset switch. It'll input of 1, which is essentially just the voltage is present. And then it's going to feed into one larger NAND gate, which is taking the second flip-flop's Q value and the fourth flip-flop's Q value, putting it through a NAND gate, and then it feeds into as the input of another NAND gate, using another input of 1 through a set of NAND and NOT. Then that'll feed into the second NAND that was originally with the switch. And then this is essentially just going to function as an AND, and that's what clears the flip-flop switches so that it will reset at 10. And it won't show 10, but it'll show 9. Also class, this will be on the final. The reason it's Q2 and Q4 is because that is when it will output 9. So that is why it's feeding in Q2 and Q4 so that it'll properly reset.
This is the increment switch. This is the reset switch. These are the 4 JK flip-flops. These are the 2 NAND gates and the NOT gate. And these are the 4 LEDs that light up to show the binary count.
Bring the action.
I wanna scream and shout and let it all out. And scream and shout and let it out.
Alright, and sending now. Alright, begin. Oh, it's smoking! It's smoking!
And let it all out. And scream and shout and let it out. We say
We're all falling and we need a place to hide. A safe place somewhere in the woods we can start a fire.